All right, well, hello everyone, and welcome to this final exam review session. So here's our goals for today's video. First, we will review some of the main topics that you may see to help you prepare for the final exam. We'll also go through brief format and procedures for the exam, and you'll notice that the format and procedures are very similar to what we had in exam 1 and 2. Finally, we will review some of the key topics from the study guide and end with 9 fully completed practice problems. So I highly recommend that as you go through this video, make note of any topics that you might still be rusty on. And also, I recommend that rather than watching me do the practice problems, I recommend that you watch this video with pen and paper in hand. And when you get to the practice problem part, I highly recommend that you pause the video and try the problem yourself. And verify that you're able to complete the problem yourself without relying on your book or your notes for help. That's a really good way to make sure that you understand these topics. And if there's something that still doesn't make sense, or if you find that something is still difficult for you, then definitely take advantage of the opportunity to get help and ask questions before the final exam. I also highly recommend reviewing some of our past videos and past lecture notes for extra practice. So here's what to expect in terms of final exam format. And you will see that this format is very similar to what we had in our previous exams in the class. We'll have some short warm-up questions initially, followed by the short answer questions, and finally 2 or 3 longer questions. And please note that approximately half of the final exam will be based on the old material from exams 1 and 2, and approximately half of the material will be new material that we have covered since exam 2. Also, as a reminder, make sure you always show all your work for the longer questions in order to receive credit. And if you'd like further practice, definitely be sure to review our study guide and past practice exams for representative questions. I've included this slide with each of our exam review sessions, but I think it's worth including one more time for this exam. My biggest recommendation on how to prepare for the exam is to study by doing problems. Please make sure that you prepare for the exam by practicing problems yourself. Reading your notes or watching videos is not going to help you develop the problem-solving skills you need. Remember, you are being tested on your ability to solve circuits problems. Therefore, to prepare for this exam, you should do practice problems. Build your intuition, and make sure that you are comfortable using the tools we've covered. While it's not possible to practice every possible version of every possible problem, if you practice the problems that allow you to learn the skills you need, you will improve and you will be prepared for our exam. So my highly recommended approach is to go back through our blank lecture slides and our blank handouts for each topic on the study guide. Rather than reading through your notes, instead pretend it's the exam. Try each problem from lecture and from the homework as if that problem was on the final exam. Pretend it's the exam and that you don't have your notes handy or your textbook handy. Pretend it's just you and that problem. See if you can complete those problems easily without checking your notes. If you find that you can complete that problem easily on your own, within no more than 10 to 15 minutes, you probably know that topic well. If you find that you do need to check your notes, or you find that you have difficulty, that's a topic you need to review further. Or feel free to reach out in help hours as well if you want to ask more questions. Also remember that we have all our practice problems discussions and resources in Canvas, which you can use for additional practice. And there's also many practice problems in our book. And finally, I just would like to remind everyone that the biggest mistake I tend to see that students make is I see that students sometimes do not know the material well enough themselves because they've relied too heavily on notes, the book, or other resources. So in preparing for the exam, make sure you understand the material well enough that you can do the problems by yourself on your own. That is the best way to test yourself and ensure that you fully understand the material. All right, so with that, let's go ahead and review each topic on our study guide. And what we'll do in this next part of the review session is we'll briefly go through the main key points from the study guide. All of these slides are slides you have already seen in our previous videos. So as you see each of these slides, I recommend that you write down any equations or topics that you may want to review further. So first thing is unit conversions and sign conventions. Make sure you're very careful about sign errors and also units. And remember to pay attention to the passive convention. Remember to satisfy passive convention, current must enter the positive voltage terminal. And if the passive convention is satisfied, a positive power means that power is being absorbed, and negative power means that that element is supplying or releasing power. Next comes our questions of the day. Once again, I guarantee that at least one question that we covered at the beginning of class will reappear on the exam in some form. And I might also be lazy and reuse or slightly modify a question from lecture or the homework. So it's a really good idea to review the questions and examples from lecture and from our homework assignments. I choose those questions for a reason. Often the questions in our homework and in lecture are good examples that illustrate the topics well. The next item on our study guide is DC circuit analysis. So these are all the skills that we covered in the first part of the class before exam 1. But you'll remember that many of our DC circuit analysis tools can also be used to solve AC circuits when we're in frequency domain and with impedances. So you may see that you might be asked to use a favorite DC tool like superposition or source transformation on an AC circuit. So definitely make sure you know how to use the tools listed on this slide. All of our favorite DC tools like Kirchhoff's laws, Ohm's law, being able to simplify resistors, capacitors, inductors, and impedances. Also current division, voltage division, node and mesh equations. We had our recipes for solving first and second order circuits. While I'm probably not going to ask you to do all 10 steps of one of those recipes, I could ask you a question about those recipes. Norton and Thevenin equivalents are also very important, both in AC and DC circuits. And source transformation and superposition are also fair game. You'll remember that maximum power transfer theorem is one of the new theorems that we covered for AC circuits. So there's a good chance that I'm going to ask something about maximum power transfer theorem. Also, make sure you understand how to simplify switched circuits. Remember when we have switched circuits and we want to calculate capacitor voltage or inductor current at the instant before or the instant after a switch is flipped? And definitely being able to simplify series and parallel inductors, capacitors, resistors, and sources. It's also very important that you remember how to deal with circuits that contain opens and shorts. Remember, if you have a resistor or any component that is in parallel with a short, that short acts like a plain wire. By definition, a short always has 0 volts across it. So if you have any other components in parallel with a short, those components will have 0 volts across them. Similarly, if you have a resistor or something else in series with an open circuit, remember that an open circuit by definition has 0 current flowing through it. So if you have anything in series with an open circuit, you're going to have 0 current through that part of your circuit. Definitely don't be afraid to draw pictures and stick figures and arrows as needed in order to recognize how your current is flowing. It's very important to know how to treat circuits when you have open and short components. Now remember, we also learned about steady state and transient behavior. Remember that steady state means not changing with time, while transient means we are changing with time. We may use the notation in some problems, as we learned, where the time just before t equals 0 is called t equals 0 minus, and the time just after t equals 0 is called t equals 0 plus. Definitely make sure you remember these points about inductors and capacitors. Remember, under DC conditions, a capacitor will act like an open circuit, or a broken wire, and an inductor will act like a short circuit, or a plain wire. Also remember that an inductor's current and a capacitor's voltage cannot change abruptly or instantaneously. These 2 points are very important to remember if you need to solve a switched circuit problem or find an initial condition. Next is first-order circuits. And you'll remember we learned an important shortcut for first-order circuits. If you see a circuit that contains just a resistor and an inductor, or a resistor and a capacitor, that circuit is a first-order circuit. And a good question to ask yourself is, does my first-order circuit have a constant or a non-constant source? If you have a first-order circuit with a constant source, one of the easiest ways to solve that circuit is to use that Norton-Thevenin shortcut that we learned. You'll remember, if we have a first-order circuit with a constant source, all we need to do in order to solve that circuit is to find the Thevenin or Norton equivalent of the circuit attached to the inductor or capacitor. Once we know our Thevenin or Norton equivalent, we can substitute into those shortcut equations in order to find our capacitor voltage or our inductor current. So if you see a first-order circuit with a constant source, you should be immediately happy because you will know right away that this shortcut equation could be a useful tool. However, if you do not have a constant source on your first-order circuit, then you'll need to solve that first-order differential equation in order to determine your desired unknowns. So just a reminder, if you have a first-order circuit with a non-constant source, then you may need to solve that first-order differential equation using our 10-step recipe. And so, while I'm probably not going to ask you to solve this full recipe, it's certainly fair game for me to ask you questions about this recipe. So you'll want to make sure you're familiar with these steps, and you might find it helpful to review our past lecture notes or homework problems to refresh your memory. Similarly, if we have a second-order circuit, that's a circuit with a resistor, inductor, and capacitor, then in that case, we would need to use our second-order recipe in order to solve a second-order differential equation. You might find it helpful to review this recipe and also some of the examples we did in lecture. There's probably not enough time for me to ask you a full second-order circuit question, but it's certainly fair game for me to ask you about some parts of this recipe. The next item on our study guide is AC circuits. We covered AC circuits a little bit in Exam 2, but we learned about how to use our DC tools with AC circuits after Exam 2. So you'll definitely want to make sure you're comfortable working with complex numbers in both rectangular and polar forms. And you're definitely going to need to be able to convert circuits between frequency domain and time domain. And remember, now we know all these other tools, like Thevenin and Norton, superposition, and source transformation. So it's certainly possible that I might ask you an AC circuit question requiring superposition, Norton or Thevenin, or source transformation. So you should know how to use your favorite DC tools with AC circuits. A good starting point would be to review the questions in our past homework assignments and in our lecture notes. Also, you'll want to make sure you remember those equations relating the different parameters for capacitors and inductors. It's still fair game for me to ask you something about the amount of energy stored in an inductor or a capacitor. One thing to note about these AC circuit questions is that the questions will be designed to be completable within the exam timeframe. So if you do need to convert numbers between rectangular and polar form, for example, please note that these manipulations will be designed to be finishable by hand within the exam timeframe, assuming that you are well prepared. So if you do need to convert between rectangular and polar forms, remember that you will need to show your hand calculations. So you might find it helpful to review these conversion equations in order to convert between polar and rectangular forms. So make sure you're very comfortable doing math with complex numbers. By now, this should be a little bit more natural for everyone, but if you need, feel free to review our previous lectures on phasors and AC circuits. And remember to follow these rules when you are performing addition, subtraction, multiplication, and division. One of the important topics we covered in AC circuits was impedance. You'll remember that impedance is analogous to resistance in a DC circuit. Impedance is the ratio of our voltage phasor to the current phasor. So definitely make sure you know how to calculate impedance for resistors, capacitors, and inductors using these equations we've learned. It's also very helpful to remember that math relation in order to convert 1 over j to negative j. Also remember that we can use all our favorite DC tools with AC circuits and impedances. So if you haven't already done so, I would highly recommend going back through our AC circuits lectures after Exam 2 and practicing some of those DC tools when we revisited them. You'll remember we learned about how we can use Ohm's law, current division, voltage division, series and parallel impedances, and all of our favorite DC tools like superposition, Thevenin, and source transformation. So make sure you remember how to use these tools. We also covered two particular types of op-amps in AC circuits. So make sure you know how to recognize whether you might have an inverting or non-inverting amplifier. And remember that if you do happen to see one of these, you can use the known op-amp equations in order to help simplify and find that ratio of output to input voltage. We also learned about the frequency response. And we learned that the frequency response describes how a circuit's behavior changes when we change the input frequency of our AC signal. We use the network function h of omega in order to describe our frequency response. So if you're asked to find the gain or the phase shift or the frequency response, you should be familiar with these equations. Remember that typically it will be given in the question what the output and inputs of interest are. So to find frequency response, we typically just convert our circuit to frequency domain, and we derive an expression for the y and x terms as a function of omega. We also learned about AC power after Exam 2. So there's a very good chance that you're going to need some of these equations on the final exam. You'll remember that we have this nice shortcut equation for instantaneous power. This comes from our trig identity when we multiply two cosines together. So definitely remember that instantaneous power has a term corresponding to average power, which is not time-dependent, and we have that time-dependent sinusoidal term. And remember, if we happen to know the magnitude and phase angle of some sinusoids, it's very easy to plug in a known v of t and I of t to determine instantaneous power. We'll do an example of this a little bit later. We also learned about complex power after Exam 2. So it's very likely that you're going to need some of these equations on the final exam. You'll remember one of the quickest ways to find our complex power is to use the equation S equals VI star divided by 2. Here V is our voltage phasor, and I is the current phasor across the component of interest. So make sure you remember to plug in the V and the I across the component that you want. V and I will not necessarily be equal to the source voltage or source current. It will be the voltage or current across the component you want to find S for. Also remember to take complex conjugate when you see that asterisk. We also learned about the physical significance of complex power. And make sure you remember the physical significance of each of these terms. Most important is our real power, P. Remember that this P is the same P as the average power for our AC and instantaneous power. So P is the real power, which is the real component of complex power. Remember, most of the time, we want to maximize our real power P in order to get as much useful power as we can. We also learned about the different cases that we can see when working with complex power and our power factor angle. Our ideal case is when our power factor angle theta is 0. This is when our current and voltage are perfectly in phase, and our voltage phase angle and current phase angle are equal. In this case, our power factor will be 1, and our load will behave like a resistive load, and our complex power will actually be 100% real. But most of the time, we are unable to achieve this ideal case. Typically, we end up being in this lagging case. In the lagging case, we see that our reactive power Q is positive and our load will have inductive behavior. Another important thing to remember is that we always need to specify leading or lagging when we report our power factor. Remember, the power factor is a very important quantity given by cosine theta v minus theta I. It helps tell us how much of our power will be real versus imaginary when working with complex power. But because cosine is an even function, we need to specify whether the power factor is leading or lagging. So if you see a power factor on our final exam, make sure you remember how to determine whether that power factor is leading or lagging. Or if I give you a power factor, you should know how to determine the phase angles of our current and voltage, knowing a power factor value and its leading or lagging behavior. If you need a review of this, make sure you check out our previous lectures on complex power. We also learned about power factor correction. We learned that if we have a load with lagging behavior, we can follow the steps shown here and apply a parallel capacitance. If we follow this recipe, we can correct the power factor of our load to be a desired value by applying a parallel capacitance C. So if you see a question asking about power factor correction, you should instantly be happy because you will know exactly which approach to follow in order to correct that power factor. Another very important topic we covered was revisiting the maximum power transfer theorem. You'll remember in AC circuits, maximum power transfer is fairly similar to what we learned in DC circuits. If we want to transfer maximum average power between an AC source and a load, we need the impedance of the load to be equal to the complex conjugate of the Thevenin impedance of the source. If that condition is met, then we know that the maximum average power we're able to transfer will be given by the equation shown here. There's a very good chance I'm going to ask you something about maximum power transfer theorem, so please make sure you remember these equations. And if you see that question on the exam, you should instantly be happy and have a good idea of how to proceed, knowing these two important equations here. Finally, our last main topic for AC circuits was transformers. We learned about this transformer toolbox. For the purposes of our class, we are able to assume that our transformers have ideal behavior, meaning that the coupling coefficient is 1. Given that ideal behavior, we are able to use the equations shown here to predict the behavior of our transformers, given their voltages and currents. So make sure you remember how to use these transformer toolbox equations. If you need, definitely go back through our lecture examples and homework questions as needed. Finally, the last topic we covered in the course was devices. So you should expect to see some multiple choice or short answer questions related to the topics we covered in devices, especially about semiconductors, diodes, and power distribution. Other topics from labs, such as filters, are also fair game. So make sure you remember those topics that we have covered. Also, there may be some multiple choice questions or a short answer question related to our labs. And all of the labs we've had in this course are potentially fair game. Please make sure that you are comfortable with the topics that we've learned, including breadboarding, filters, tolerances, and the devices topics. So now that we have covered all of the general review of our study guide, let's now go through some practice problems. In this video, we will go ahead and go through all 9 of these practice problems. And I highly recommend, in this case, that rather than watching me do the problems, I recommend that you pause the video and try the problems yourself. See if you can get them correct. If you find that a problem is difficult, or you're not sure how to approach it, that might be a topic you need to review further. So please use these practice problems to help you identify topics that you might need to review more, and also use them to help you review skills that you might see on the final exam. Make sure you are familiar with all the topics covered in the study guide, as the topics listed in the study guide are the ones that will be covered on the exam. Let's go ahead and start with practice question 1. Here we have a bridge circuit, and we are being asked to find the voltage across the 30 ohm resistor. Take a moment and pause the video if you'd like, and then you can check out your answer against mine. So there's many possible approaches for this practice question, but my recommended approach is to use voltage division. In this case, you can recognize that this 10-volt source basically has current flowing in 2 parallel paths. One path is going kind of counterclockwise around the top portion, and the second path is going clockwise around the bottom portion. In this case, we can recognize that the 30 ohm resistor and 120 ohm resistor must together experience a 10-volt voltage drop. Another way to draw this circuit is to draw 2 sets of parallel resistors. And if you walk around this circuit in both loops, you'll recognize that this is indeed an equivalent circuit. So in this case, given that both the 30 ohm and 120 ohm resistors must experience a 10-volt voltage drop, we can actually consider those resistors separately. So let's go ahead and call this my voltage V30. If I'm just trying to find the voltage across that 30 ohm resistor. If this were an exam question, I would probably give you a specific polarity just to avoid confusion. But here, let's go ahead and just assume our polarity is as shown. So in this case, I can simplify this circuit down to something like this. Because I know both the 30 ohm and 120 ohm resistors experience that 10 volt drop. So this basically becomes a voltage division problem, where the voltage across my 30 ohm resistor is going to be equal to that resistor's resistance divided by the sum of all the series resistors times the voltage of the source. So this gives us 30 over 150 times 10 volts, which is the same as 315 times 10, and that gives us 2 volts. One thing to watch out for here is, had I asked for the voltage across the 30 ohm resistor like this, notice voltage division would have given me the opposite polarity, because I assume current enters the positive terminal. So if you do see that your polarity is opposite what you want, you would need to multiply by -1 in order to get the correct polarity. In this case, I'm just going to go ahead and assume I was looking for the voltage drop from that 10 volt source. I'm just going to leave the polarity like this. All right, in our next practice question, we are being asked to write a mesh equation for the loop containing current I2. So in this case, you'll want to remember how to write a mesh equation. And typically, the thing you want to remember is you'll want to walk around the circuit and apply Kirchhoff's voltage law. And then rewrite the voltages in terms of the mesh currents and resistances. So let's give this a try. So in this case, we want the loop containing I2. I'm going to go ahead and walk clockwise around my circuit, starting in the lower left corner. And I'm going to go ahead and apply Kirchhoff's voltage law. And I'm going to follow the bank account convention that we covered back in the beginning of the course. If I do this, I'm going to treat the voltages across my resistors as drops. So I will have minus V 200 ohms for the voltage across that 200 ohm resistor. Then I'm going to gain 2 volts because I am going from the negative to the positive end. Then I lose 300, the voltage across that 300 ohm resistor. I'm going to call this 100 ohm resistor number 1, and then minus V 100 ohm, comma 2 for the second one. Now I need to rewrite these voltages in terms of the mesh currents. So in this case, I have that mesh current I2 as well as I1 and I3. The voltage across this 200 ohm resistor, that depends completely on I2 alone. So we have negative 200 ohms times I2. 2 volts stays as is. And the 300 ohm resistor also has I2 flowing through it. But notice our 100 ohm resistor. That resistor has I2 flowing through it, but also I3 going the opposite way. If you're not sure how much is actually flowing through the resistor you want, you can also draw a little picture and apply Kirchhoff's current law. And you could recognize in this case that plus I2 minus I minus I3 equals 0, and you could determine that your current is just going to be I2 minus I3. So when in doubt, you can apply Kirchhoff's current law to help. In this case, that will give us 100 ohms times I2 minus I3 for our first 100 ohm resistor's voltage. And the second 100 ohm resistor's voltage will be 100 times I2 minus I1. And that will give us our completed mesh equation. Notice that unless I specifically instruct you to solve for the mesh currents, it would be correct to leave the mesh equation in this form. All right, let's move on to our third practice question. And in this question, we are asked to find the Thevenin voltage and Thevenin resistance for the circuit connected to our inductor. And specifically, this is when the switch is closed. So let's go ahead and find that Thevenin equivalent. A good first step here would be to draw the circuit with the switch closed and also with the inductor disconnected. Because in this case, we specifically want to find Thevenin voltage and resistance for the circuit that is connected to that inductor. So if we go ahead and draw this circuit, notice if the switch is closed, nothing is going to go through that 2 ohm resistor. Notice our inductor was attached. The inductor was here, but right now we only care about the circuit that was attached to the inductor. So in our case, we end up with a 12-volt source, 4 ohm resistor, and 6 ohm resistor. Notice nothing goes through that 2 ohm resistor due to the presence of the short when the switch is closed. So the first step when we do our Thevenin voltage calculation is to find VOC, or the open circuit voltage. Here, VOC is going to be equal to the voltage across that 4 ohm resistor. So to find the voltage across that 4 ohm resistor, one nice approach is to use voltage division. And in this case, we have 4 ohms divided by 4 ohms plus 6 ohms times 12 volts. That gives us 4 divided by 10 times 12, or 4.8 volts. So now we have found our Thevenin voltage. To find Thevenin resistance, we turn off the independent sources. And remember, if we have a dependent source, we connect the VEX with current IEX, and then find VEX over IEX. If there's no dependent source, we simply find the equivalent resistance when walking from one open terminal to the other. So in this case, we do not have a dependent source, we just have independent sources. So we have a slightly nicer approach. So since we have no dependent sources, we can just turn off the 12-volt voltage source. Remember, voltage sources are replaced with shorts, current sources are replaced with opens. And we get something like this. So notice we need to walk from A to B, and notice there are two parallel paths. So here, our Thevenin resistance will be the 4 ohm resistor in parallel with the 6 ohm resistor. So in this case, if we use our shortcut equation, we determine that our Thevenin resistance is 2.4 ohms. And there you have it. Notice, had we had a current source instead of a voltage source, our approach would have been slightly different, because we would have needed to turn off the current source and replace it with an open. And if we had a current source instead of the voltage source, then our calculation for Thevenin voltage also would have been different. So if you're a little bit rusty on Norton and Thevenin calculations, make sure you review our lectures 7 and 8 videos for additional practice. Let's now try a maximum power transfer practice. In this question, we are being asked to find the maximum power which could be delivered to the load in the circuit shown. So if you see a question asking something similar, you should be immediately happy, because you should remember maximum power is transferred when the Thevenin equivalent of our source, complex conjugate, is equal to the impedance of our load. And in this case, we know what the Thevenin impedance of our source is. In this case, the Thevenin impedance of our source is just going to be that 400 ohm resistor plus j omega L. In this case, omega is 1000. and our L value is 0.8 henries. So the Thevenin impedance of our source is 400 plus J800 ohms. So in this case, for max power transfer, our load must have the impedance 400 minus J800 ohms. And if this condition is satisfied, then we can find P max using our second equation. So in this case, the maximum average power that we'd be able to transfer will be 1/8 times 5 volts squared divided by 400 ohms. Remember, 5 volts is the magnitude of our Thevenin voltage, and 400 ohms is the real part of our source's Thevenin resistance, or real part of our source's Thevenin impedance. This gives us 25 divided by 8 times 400, which is 0.0078125 watts, or about 7.8 milliwatts. All right, our next practice question is one of the examples we did previously on transformers. And so in this example, we have a circuit with an unknown turns ratio and an ideal transformer. We know our voltage source, and we know that we have a 5 milliamp current in our secondary coil. And so we're asked to determine our turns ratio, the equivalent impedance felt across the primary coil due to this 10,000 ohm resistance in the secondary, and we want to find our current I1 supplied by the voltage source. So you'll remember a good question to ask yourself first is, what do we know? And in this case, well, we know quite a few things. Let's label our transformer in the same way as our toolbox equations. And so that means we have our voltage V1, V2, and we have our current I2 and I1. So what do we know? In this case, we know that our voltage V1 is just 10 volts, because that's the only thing next to our voltage source. We do not know I1. What else do we know? Well, we don't know V2, but we do know I2 and Z load. And in this case, I2 we're given as 5 milliamps, or 0.005 amps, and we know Z load is 10,000 ohms. So we can determine that V2 is 50 volts. And then finally, I2, we do in fact know I2. I2 is just negative 0.005 amperes due to the direction. And finally, N, our turns ratio, is unknown. So in the first part of the question, we're being asked to determine our turns ratio. So the first thing we want to ask ourselves is what toolbox equation for transformers relates our turns ratio n to stuff we know? And in this case, notice that we know V1 and we know V2. And so knowing both of those things, we can write that based on our toolbox equation, V1 is going to be N1 over N2 times V2. Or we can write that 10 volts equals 1 over N times V2. And since V2 is 50 volts, we determine that our turns ratio N must be 5. Alright, so we finished the first part. Next part is to find the equivalent impedance felt by the primary coil. Well, that part alone gives us a big hint about what equation we need to use. Because remember, we know from our toolbox, we can replace that whole transformer with an equivalent impedance, where this equivalent impedance is 1 over N squared times Z load. So if we go ahead and plug that in, notice we'll determine that the equivalent impedance will be 1 over 5 squared times 10,000 ohms. So if we math that through, we'll determine that the equivalent impedance felt by our voltage source in the primary coil, that's just going to be 10,000 divided by 25, or 400 ohms. Finally, our last step is to determine our current I1. And there's multiple ways to do this. We could use I2 and N with the toolbox equation, or use V1, Z equivalent, and Ohm's law. Here I'll go ahead and use the toolbox equation with I2. We know from our toolbox that I1 must be equal to negative N2 over N1 times I2. So that means I1 must be negative 5 times, notice the signs here. Remember, I2 is negative 5 milliamps because it is going in the opposite direction as given in our question. So therefore, we determine that our current I1 is 0.025 amps, or 25 milliamps. All right, let's move on to our next practice question. This question is similar to one that you may have seen in the homework. Here we are given that we have a circuit with an unknown impedance, but we do know our voltage phasor, and we're given an apparent power. Remember, that is, if we write our complex power as S angle theta, apparent power is the magnitude of our complex power. We are also given a power factor of 0.8 lagging. So we're being asked here to find how much current is exiting our source and to determine the unknown impedance. So a big hint here is the apparent power and power factor. Because what we can do is we can use the power factor to get our power factor angle. And then once we know our power factor angle, we already know our apparent power. So we know our complex power S will be the apparent power angle theta, where theta is our power factor angle. So let's first ask ourselves about our power factor. We are given that our power factor is 0.8 lagging. What this means is that 0.8 is equal to cosine theta v minus theta I. And this also tells us, if we take inverse cosine, that theta v minus theta I must be either positive or negative 36.9 degrees. And since we are lagging, remember that also gives us a hint as to our behavior. If we let theta v equal 0 degrees, we know, if we're lagging, that theta v minus theta I must be greater than 0. That gives us theta I is equal to negative 36.9 degrees. Alright, so now we know our theta I value. And we know our overall theta v minus theta I value. So now that we know this, we can plug it back in for our power factor angle. We can determine, since we know our apparent power is 50 volt amps, we can determine that S must be equal to 50 angle 36.9 degrees because our power factor angle, theta v minus theta I, is equal to 0 minus negative 36.9, or positive 36.9 degrees. So now we know our complex power S. Our goal, however, was to determine current exiting our source and then to find our unknown impedance. It's very important to remember that equation S equals V I star over 2. Notice we know that our voltage from the source, we know V source is 20 angle 0 degrees, and we know that S is equal to 50 angle 36.9 degrees from the source. So we can use this equation to find our current I from the source. Let's go ahead and do that. So once again, we know that S is equal to V I star divided by 2. So we can rearrange and write that I star is equal to 2S divided by V. If we substitute, that gives us I star is equal to 2 times 50 angle positive 36.9 degrees divided by V, which was 20 angle 0 degrees. So if we go ahead and solve for I star, we will determine that I star is equal to 5 angle 36.9 degrees. So if we take away the star and just find I, we'll determine that I is equal to 5 angle negative 36.9 degrees amperes. So now we know I source. We want to find Z unknown. How could we do that? Well, one approach is to use Kirchhoff's current law. By Kirchhoff's current law, we know that I source must be equal to I1 plus I2, where I1 and I2 are the current phasors through the parallel paths. So let's go ahead and use the J8 ohm and 6 ohm resistors to get I1. And then we can substitute. Then we can find I2. And once we know I2, we can use Ohm's law and voltage I2 to get Z unknown. So let's first determine I1. So we know that I1 is equal to V over the impedance across that path, which will be 20 angle 0 degrees, divided by 6 plus J8 ohms. If we convert to polar form, that gives us 20 angle 0 degrees divided by 10 angle 53.1 degrees. So if we take that division, we determine that I1 will be equal to 2 angle negative 53.1 degrees amperes. Now that we know I1, we know that I2 will be equal to I source minus I1. That gives us I2 will be equal to I source minus I1. Let's go ahead and convert these to rectangular before we do that subtraction. So you'll see our current I, it will become 4 minus J3 amperes if we convert. And our I1 value will become 1.2 minus J1.6 amperes. So if we go ahead and subtract in polar form, we will determine that I2 is equal to 4 minus J3 minus 1.2 minus J1.6 amperes. This gives I2 is equal to 2.8 minus J1.4 amperes, or 3.13 angle negative 26.6 amperes. Now that we know I2 and we know V, the last step is to find Z unknown. We know that Z unknown will be equal to our voltage V divided by the current I2. This gives us 20 angle 0 degrees divided by 3.13 angle negative 26.6 degrees amperes. We perform that division and we determine that our unknown Z is equal to 6.39 angle 26.6 degrees ohms. So notice that this question had a number of steps, but each step was very doable. It was just important to make sure we understood complex power, Ohm's law, and Kirchhoff's laws. In practice 7, we're asked to solve for which of these circuit elements absorb 12 watts. In this case, it's important to remember the passive convention. An element is absorbing power if the power value is positive and if the current is entering the positive terminal. So in this case, we can see that choice A and choice D have positive power and current is entering the positive terminal. So in both of elements A and D, the passive convention is satisfied and we are absorbing power. Notice elements B and C are supplying power. So one thing to be careful of here is you might have noticed there is a unit change. In this question, we're being asked which of these absorb 12 watts. So you see, in fact, that choice A is actually absorbing 12 milliwatts. So correct answer here is actually not both A and D, but actually only choice D. All right, let's move on to practice question 8. In this question, we're asked to find the instantaneous power delivered by the source. So in this case, you might want to remember that we have a shortcut equation for instantaneous power that comes in handy. So remember, if we know that our voltage is some value, and if we know our current is some magnitude with a given frequency and phase angle, we can plug Vm, Im, theta V, and theta I into our toolbox equation. This is much faster than using the trig identity to derive the same result. So a good strategy for this question is to recognize that we already know V of t delivered by the source. We need to solve for I of t delivered by the source. So in this case, let's go ahead and convert to frequency domain. And we see, if we convert to frequency domain, that we can find our current I by combining our impedances. So in this case, we have our voltage, and we know our equivalent impedance is just going to be equal to our inductor with J3 ohms plus the two parallel elements, 6 ohm resistor in parallel with the J2 ohm capacitor. If we solve for Z equivalent, we'll determine that that value will be equal to 1.6 angle 60.3 degrees ohms. And then using Ohm's law, we can determine I is just V over Z, so our current I will be 7 angle 0 degrees divided by 1.6 angle 60.3 degrees, and that will give us our current I is 4.38 angle negative 60.3 degrees amperes. Using our current I, we can find that I of t will be 4.38 cosine omega t minus 60.3 degrees amperes. So now that we know our source voltage and our source current, we can plug into that instantaneous power equation. And so you'll remember that in this case, we have Vm is 7 volts, Im is 4.38 amperes, theta V was 0 degrees, and theta I was negative 60.3 degrees, and omega was 10. So if we plug in to our toolbox equation, we can go ahead and determine the following. And if we simplify, we determine that our power will be 7.6 plus 15.3 cosine 20t minus 60.3 degrees, and units will be watts. All right, our last practice question is one of our earlier examples on complex power. In this example, we're trying to find complex power delivered to the load in the circuit. And here we know that our resistor is 9 ohms and the inductor is 5 henries. We are also given our voltage source. So if you see complex power, your brain should immediately be thinking about our toolbox equations. We know that complex power S is VI star over 2. And here we know that our voltage V is just 24 angle 75 degrees. So let's go ahead and find I star. In this case, to find I star, we need to find our equivalent impedance. We know that I star will be our voltage V divided by the impedance Z in our circuit. And so if we convert our circuit to frequency domain, we see that our 5 Henry inductor will become J times 3 times 5 henries ohms, and our 9 ohm resistor becomes a 9 ohm impedance. So in this case, our current I will be given by our voltage 24 angle 75 degrees divided by 9 plus J15 ohms. If we convert that to polar form, we get 24 angle 75 degrees divided by 17.5 angle 59 degrees, which gives us 1.37 angle 16 degrees amperes. So we found our current. All that's left is to find our complex power. So just be careful of units and complex conjugates here. Remember, we flip the sign on our current phase angle because we're taking complex conjugate. And so if we go ahead, plug in, solve for S, we will determine that our complex power will be 16.44 angle 59 degrees volt amperes. The question asked for rectangular form, so we just convert back to rectangular. We get 8.47 plus J 14.1 volt amperes. And there you have it. All right, so with that, this concludes our final exam review session. I hope you found these practice problems helpful. And remember, you're more than welcome to reach out if you have any questions ahead of the final exam. Finally, I'd like to thank everyone for a great semester, and I hope you enjoyed our circuits class. Feel free to reach out if I can help with any further questions. And I hope to see you in a future course or a future video sometime soon. Thanks everyone, and take care.